last lesson of solving systems of equations that are linear equations, systems of equations. Our learning goal today is, those of you who are reading lesson 5.4 should have realized that what we're going to be doing today is we have to be able to identify and classify, in other words, name systems of equations, and we're going to do it either according to their graph or their solutions or maybe both, okay? So we have to understand that, first of all, remember that about 4-minute video that we watched one day, I don't remember if it was last week or the week before, and it talked about the different types of solutions we could get, and it showed the graphs that go with them, and it even showed some algebraic, a little bit of algebraic stuff. How many different types of solutions can we get to a system of equations? Can there be an infinite number of solutions?
No.
Actually, there can't there? Yeah. Anybody remember what the graph, or what was the situation when there are an infinite number of solutions to a system of equations?
All numbers.
Well, that means all real numbers, but not necessarily all real numbers. We have to be really careful about that, because now when we talk about solutions to a system of equations, we're talking about ordered pairs. So we're not talking about just any number on the number line. We're talking about specific ordered pairs that make both equations true. So we're going to be careful about calling it all real numbers. Instead, we're going to call it infinitely many solutions. But can anybody remember what happened on the graph when there were infinitely many solutions, Christine?
There was 2 lines on top of each other.
Yeah, there were 2 lines, but they were on top of each other, weren't they? So in other words, every point on each line intersects with the point on the other line. So they share many, many points in common. So then there are infinitely many solutions. So when you have the same line on a graph, you graph one of them and the other one graphs right on top of it, you have an infinitely many solution situation. What's the most common one that we've had happen? No solution?
Or, that's not true.
One solution. Haven't you mostly been getting just one ordered pair solution?
Mm-hmm.
Yeah. And what happens on a graph when there's one solution?
They cross at one point.
We have those intersecting lines that meet at just one point. They only share one point in common. So then there's infinitely many solutions because the lines are on top of each other, and there are many, many ordered pair solutions. There's one solution because those lines cross each other at only one location, so there's only one ordered pair solution. How about no solution? Do you think there's such a thing as a no solution to a system of equations?
Yes.
Michaela? What do you think?
Lines are parallel.
If the lines are parallel. If you have parallel lines, will they ever meet?
No.
Will they ever share a point? No, they can't ever share a point because they're never going to meet. So then there's no solution. So there are actually 3 different types of solutions. We can either get one solution, which is the most common one that we've had happen. Actually, when we were graph solving by graphing, you had a time, I remember at least one time, where you had parallel lines, which meant no solution. And I don't think you've ever had the time yet when there are infinitely many solutions, or in other words, the third choice, okay? Well, here's what we have to do then. Since there are 3 solutions, we are going to have to decide how are we going to find out without actually graphing them, how could we find out what type of solution it would have? And then not only that, but what classification can we give it? In other words, we now have to name those systems. Okay, how many of you have a first name and a middle name? Everybody in here, I do too. I have a youngest daughter, though, that I didn't give a middle name. Like, for some reason, I just decided that with her name, a middle name didn't go very well, and we had a longer last name, so I thought, you know what? She's just not going to get a middle name. So she just has a first name. Bugs her to death, but you know what? That's what her mom did to her. Okay, so when we have these classifications for these systems, we're going to find out that some of the systems have a 2-part name, a first name and a middle name, and then there's another system that only has a first name and no middle name, like my daughter, Ricky.
Would it be a consistent system?
Yeah, so a system with at least one solution, we are going to call a consistent system. And notice what it said, with at least one solution. Well, that means we have the intersecting lines one where there's one solution, that's at least one. Or we have the lines on top of each other where there are many, many, many ordered pairs. So we have two situations that can be considered consistent. Ricky,
Could it ever be 2 points on a line, but not more than that?
what do you think? Do you think two lines could ever just meet at 2 points?
Like go like this and then through a portal and come out and
Wow.
I don't think so. I think we're either going to have one solution if lines meet, or we're going to have infinitely many solutions if lines meet, but we can never have any other type of situation. Yeah. So when we have, here are the two types of consistent. We have the independent type. So this is the middle name for that system. We have a consistent system that is also independent. So it's a consistent independent system. That's when it has exactly one solution. That type of system has the one solution. Well, we already know lots of stuff about that. When you graph those type, what happens? What kind of lines do we have? Intersecting lines, yeah. The graph will have intersecting lines. They don't have to be perpendicular. All they have to do is intersect. Well, if lines are intersecting, what has to be true about their slopes?
They're different.
Do they have to be opposites?
No,
Do they have to be reciprocals?
no, they have to be different.
All they have to do is be different. It does not matter as long as they are different. Because what would happen if they were the same?
They would be the same line.
They might
Or
be the same line
or
or
parallel.
they might be parallel lines. So if they're going to intersect, they have to have different slopes. They don't have to be opposites. They don't have to be reciprocals. No, they just have to be different. When we solve one of these algebraically, what happens? If there's only one solution, what happens when we solve it algebraically? Morgan? You get an ordered pair solution, yeah. So in reality, we have mostly been working with consistent independent systems. So that's one of our types of systems, one of our possible solutions. Well, the other one that gets at least one solution and is consistent is a dependent. So here's the middle name for that one. So we have a consistent dependent system also. That's our one that has infinitely many solutions. Think about being independent. When you're independent, you don't want your parents to have anything, you don't want them telling you what to do or making any decisions for you. It's me, myself, and I. You just are number one. You don't care about anybody else when you're independent. Independent, one solution. Dependent, oh yeah, when you want their money, or you want to ride somewhere, or you want them to buy you some clothes, then you're pretty dependent upon them, and you would follow them anywhere, wouldn't you? So infinitely many solutions is dependent, okay? So what happens on a graph? What did we say? Has what? What's true about the lines?
The
Same line, yeah. The graph has same line. In other words, you graph one, you graph the other one on top of it. It really looks like you only have one line because it is in the same location. Well, what has to be true if they're going to have the same? Are their slopes? If they're going to be the same line? What has to be true about their slopes and their y-intercepts?
They have to be the same.
They have to be the same. So the slopes and y-intercepts are the same. In other words, the slopes match each other, the y-intercepts match each other. Here's another name that you'll actually hear maybe more of in geometry. When you have a line and another line that graphs right on top of it, we call those coincident lines. Coincident. Isaiah.
You were saying earlier that we will deal with this in geometry. Will we be dealing with it in this lesson too?
Coincident lines. I just want you to keep in mind that when you have those infinitely many solution ones, that means the same line graph. Just keep in mind that those lines are just called coincident lines, okay? Ricky?
Do we have to take geometry?
No, don't go there right now. We don't have time for that. Solved algebraically. Solved algebraically. Both variables will eliminate. So you're using the substitution method or you're using the elimination method. In the process, both the x and the y are no longer available to be solved for. They both eliminate. And you end up with an equality. Equality meaning whatever you end up with on one side is the same as what you end up with on the other side. One side is equal to the other, you end up with a true statement. So this happened back in chapter 4 when we were working with linear functions. Sometimes we were solving for a linear function, solving for x. The x disappeared, it eliminated, but we ended up with a statement such as 3 equals 3. And when that happened with a linear, with just one line, we said that was the solution was all real numbers. That was the all real number solution. Well, when it happens now, when there are two equations working together, when that happens now, the variables eliminate, they're both what x and y end up eliminating, and you end up with a true statement and equality. Now we say, oh, that means there's infinitely many solutions, many ordered pairs. Not any ordered pair on the graph, but many ordered pairs because they share many points in common. So right there we have two types of systems. We have the consistent independent. How many solutions with that one? Independent. One solution. Consistent dependent. How many solutions? Infinitely many solutions. Okay, well then what happens with our third situation when there's no solution? We call that an inconsistent system. Yeah, an inconsistent system. That's the one that only has the first name like my daughter, no middle name. It's an inconsistent system. That's it. Whine all you want system, you're not getting a middle name. Just like my daughter. You can whine all you want, you're not getting the middle name.
What's
So
her
your
name?
daughter's
Now, I will tell you what she's done.
your daughter's
Since she's now an adult, married with children, she kept her maiden name and called that's her middle name. And then her married name is her last name now. So she got her way in the end. But so when there's only one name, it's the inconsistent system. Okay? We can talk more about my daughter later. We got to do this. Okay? So the graph has what's going to happen when there's no solution? What kind of lines? Parallel. We already identified that a little bit ago. Parallel lines. If you have parallel lines, they are never going to meet. They're never going to share a point in common, so there's going to be no solution. Well, what's true about parallel lines? What's true about their slopes?
They're the same.
Same slope. And what's true about their y-intercepts? Different y-intercepts. And we're identifying all of this stuff because you know what? When you have to prove without graphing a system, what type of system it is, you're going to use this kind of information to help you out. When you solve these algebraically, guess what happens to the variables?
Eliminate.
They eliminate again. And just like back in chapter 4 when we solved one equation and the variable eliminated, if we ended up with a false statement, we said no solution. In other words, there was no number on the number line that would make that true. This is the same thing. If you end up with an inequality, or in other words, something that does not equal something else, you have a no solution one. There are no ordered pairs that are going to make that true. Okay, in summary though, before we move to the backside and practice, what you're going to actually be doing in your homework, let's name the three types of systems. What's one of them?
Consistent.
Consistent what? Remember, a consistent one has a middle name. Independent. Consistent, independent. If you're consistent, you got a middle name. So my oldest daughter and my son in the middle, they got middle names. They're consistent. Okay? Consistent, independent. What's another type? Riley?
Consistent, dependent.
Consistent, dependent. So in other words, a first name and a middle name. And what's our third type of system? Class?
Inconsistent.
Inconsistent. The first name only. So when you are instructed to classify a system, it's going to be one of those three. All of them have a classification. You just got to figure out what its classification is according to its solutions or its graph or something that'll help you out. Okay, let's go to the backside now and let's start practicing the types of things that are going to happen in your homework. We're gonna practice a method 1 and a method 2 for every type, but you only have to do either method 1 or method 2. You get to pick. And you can change off between problems. And some of them you can do method 1, and other ones you can do method 2. But you need to do one or the other to prove what they want you to do. It says here, show that that system of equations has one solution. So we're going to practice both so that you have your notes to refer to. Please have your notes out when you're doing your homework. Okay? Isaiah.
Will all the questions in your book be in slope intercept form?
Not always. Are they in this first one?
Yeah.
Okay, they are in this first one. So guess what? When they are both in slope intercept form, I think you're going to realize which method is going to be more efficient to use. Okay? So here's method 1. If you use method 1, you're comparing the slopes and the y-intercepts, because by comparing the slopes and the y-intercepts, not even having to graph it, just comparing their slopes and y-intercepts, you're going to be able to say, oh, here's what kind of lines I would have. If that's the kind of lines I have, this is what kind of solution I have. This is the kind of solution I have, this is what kind of system I have. So, just like I always make you do when you're graphing, I always say, identify M and B. So you need to identify M and B. Both of these are in slope-intercept form, so pretty easy. What's our slope for the first one?
-2.
-2. And what's its y-intercept?
2.
2. Okay. How about the other equation?
3.
Its slope is a -1, its y-intercept is 3. Okay? So after we've shown that, we've identified it, we've written that down on paper, now we say, we're going to write out, oh, here's what I observe about the slopes. Are they the same or are they different?
Different.
Different. So I'm going to say, you know what, there are different slopes. I've just done some of our writing for us. Different slopes. You know what, if their slopes are different, do we even care about the y-intercept? Because what do different slopes tell us?
That they're not parallel.
Thus different lines.
Unless they're intersecting.
Intersecting lines.
Intersecting lines.
If they have different slopes, there's only one possibility. Those lines are intersecting lines. And if they are intersecting lines, now we know what kind of solution it would have.
1 point.
One solution. If there is one solution, what kind of system do we have?
Consistent.
Consistent, independent, consistent, because we found a solution, we found at least one solution, that makes it consistent, and we only found one. Remember, when you want to be left alone, me, myself, and I, it's 1. Okay, that's using that method. So do you understand everything you would need to show? Well, if you choose to use method 2 is solving it algebraically. We know 2 ways to solve algebraically now, substitution and elimination. So which of those 2 methods would be most efficient, or one we could use in this one? William? Substitution or elimination? Substitution. They're not in standard form, are they? No. This is a good one for substitution. So we will, let's take the first, both of them are equal to y. So we're saying y is the same as -2x plus 2. So -2x plus 2 is working together with this other equation for y. It's going to take the place of y in that other equation. So we have -2x plus 2 going in for the y in the other equation, and our -x plus 3 that it is equal to. Go ahead and solve that, because you know how. Go ahead. I got x equals -1. You got it? Okay, so let's go solve for y now.
Oh.
So we're going to use either equation, doesn't matter which one you use, and substitute in, I think I'll use the -2x plus 2. You use the one you want, and we're going to substitute into that our x value that we just got. and get it simplified down until we can say what y is equal to.
I guess the other one got the same thing.
Okay, we should all get the same thing, right? Y equals 4 is what you should get. Y equals 4. So by using method 2 and using the algebraic method to solve it, we found out there is one solution, and what is it? This time we can actually state what it is. What is it?
-1, 4.
Negative 1, 4, which then tells us it's what kind of a system.
Consistent, independent.
Okay, consistent, independent.
But we're gonna have to try different methods, like multiple methods in each problem.
What did I say, Ricky? Think back. Did I say you had to use both methods?
No?
No, I said you get to pick, and you can, one set of problems, you can use method 1, and then you can decide, you know what, I want to use method 2 for some of these. You get to make the call.
Can
Okay.
I get graph paper then?
So, you don't need graph paper, Ricky.
Oh, because
You know, we don't really need that because we answered that already in both methods, didn't we?
Because when I looked in the book, when I was reading in the book, it said something about you could graph it too.
Sure, you can if you want to. So I guess, Ricky, if you want graph paper, you can have it, okay?
Oh.
Okay, any other concerns about proving that a system of equations has one solution? If you use method 1 and they're already in slope-intercept form, is that more efficient than the solving algebraically? I think it actually is. You just have to identify slope and y-intercept, say, oh, here's the deal. I got different slopes. That tells me I have intersecting lines. That means there's one solution. That means it's a consistent independent.
So that's all the work that you'd have to show for that.
That would be the work for that one, everything we showed right there. If you use method 1. If you use method 2, then you're actually using substitution or elimination and seeing what happens. In this case, what happened is we got an ordered pair. So we said, okay, well that tells us there's one solution. That tells me my system is a consistent, independent system.
So what would happen if you had infinitely many?
Let's find out.
Okay.
Next one. Here's a system. It says, show that that system has infinitely many solutions. Okay? So if you use method 1, remember this is method 1 is you compare their slopes and their y-intercepts. So our first equation, is it in slope-intercept form? Yeah, okay, so we can go right to saying what is its slope? 1, and its y-intercept is -3. Okay? How about that other equation? Is it in slope-intercept form?
No.
So get it there. You need to do that first. What should we do?
Subtract x.
Subtract x. Okay, we can subtract x from both sides. And we're going to have what now? Negative y equals 3 take away x. And now we're not going to divide by negative y, but we're going to divide by, I'm going to change that to add the opposite, 3 plus a negative x. And then what am I going to divide by? Negative 1, right? I'm going to divide everything by negative 1. So now my equation should be in slope-intercept form. Y equals what? What's this? -3 plus negative divided by negative is a positive x over 1 is x, right? Isn't that just x? Everything over 1 is itself, okay? So what is this one's slope?
1,
1,
-3,
and its y-intercept is -3. So now we go to saying, okay, well, the reason I did that is because I'm going to compare their slope, and if I need to, also their y-intercept. So what's true about the slope? It's the same. But I have to go a step further because if they have the same slope, there's two possibilities. They could be the same line, or they could be parallel lines, right? Okay, so now I have to compare their y-intercepts too. What's true about them? Are they the same? They're the same. Same slope, same y-intercept, thus
Same line.
same line.
Same.
Well, if it's the same line, how many solutions are there?
Infinite.
Infinitely many solutions.
Oh.
So this is what else we do. We say, okay, well that tells me then there are infinitely many solutions, which then tells me what kind of system do we have? Remember, when there are solutions, it is a consistent, for sure.
Consistent,
And if it's
dependent.
consistent, it has a middle name.
Independent.
Dependent. There's many of them, so dependent. So consistent, dependent is its classification. Consistent, dependent system we have here. So that's doing with method 1, comparing their slopes and y-intercepts as if we really were going to graph it. But yet we don't really need to. If we use method 2, we are using the algebraic way where we are going to see what happens when we actually solve it. So which method would be a good one for this one? Substitution or elimination? Substitution again, isn't it?
Mhm.
Because we have y equals, so y is the same as x minus 3. So that can take the place of the y in this other equation. Now, again, I'm going to suggest that here's what we do with that. We rename that equation as add the opposite, and because we're going to be subbing in for that y, we make that negative y a negative 1y, and we'll probably be better off. So subtracting y is the same as adding a negative y. If you have a negative y, it is really being multiplied by negative 1. Is that true? Am I misleading you? I hope not. Okay. So we have x plus negative 1, and in parentheses we're going to put in place of that y that x minus 3 that the other y is equal to, and then we'll finish our equation equals 3. Once again, I'm going to suggest changing that subtraction inside those parentheses to
And
the opposite. Carly?
What did you rename there?
I took this right here, this x minus y equals 3, and I just changed it to add the opposite. So it's a negative y now.
I made it.
And a negative y is the same as a negative 1y. And then I changed the subtraction in my expression. I substituted into, instead of x minus 3, x plus negative 3. Because then when I do the distributive property, I will hopefully do it correctly.
Mhm.
So we're going to bring down that x that's in front. It's called the tag along for the
X
moment.
plus negative x.
Negative 1x and negative x plus
3 equals
3 equals, bring down our 3 over here.
Then you just cross out that first part of 3 equals 3 and yay!
Because x plus negative x is, they
0.
cancel each other out, don't they? They're opposites. So they cancel each other out, and we end up with 3 equals 3. Is that true or is that false?
It's true.
Is that an equality or an inequality?
Equality.
It's an equality. So you know what? We have the situation where we're going to say the variable's eliminated. What we were doing was we were eliminating the y for a bit, and we did. And then in the process of doing that, we eliminated the x's also. So the variable's eliminated. And we have an equality. That is a true statement, so we can say it is an equality. Well, if that's the case, variables eliminated, we ended up with that true statement, that equality. What does that tell us? What's the solution?
One solution.
There's three
There's infinitely many solutions. Remember on the front we said if the variables eliminate and we're left with an equality, we're going to say this is an infinitely many solutions one. And if it's an infinitely many solutions one, it has a solution. It just has lots of them. So what kind is it, consistent or inconsistent? Consistent.
Deep.
And when it has more than one, it is dependent. Yeah, more than one. Dependent. So that's using method 2, solving it algebraically and proving it that way. Questions on that one? Ricky, do you have to do both ways?
No.
Okay. Go last page. Show that this system has no solution. No solution. So method 1, compare their slopes and y-intercepts. If this is the method you choose, this is what you gotta show. Is the first equation in slope-intercept form?
Mm-hmm.
Hey, what's its slope?
-2.
-2. What's its y-intercept?
5.
5. Okay? Oh, the second equation, is that in slope-intercept form?
No.
That's a pretty easy fix though, isn't it? Subtract 2x. And we end up with y equals 1 subtract 2x. Also known as
-2, 1.
negative 2x plus 1, right? Okay, what's the slope of that
-2.
one? -2. What's its y-intercept? 1. So we compare their slope. What's true about their slopes? Same slope. Well, we can't stop there. If they have the same slope, there's two possibilities. They could either be the same line or they could be parallel lines, so we have to compare their y-intercepts. What's true about their y-intercepts? Are they the same?
They're different.
They're different. So if they have the same slope, but they're rising and running at the same rate, but they're crossing the y-axis at different locations, what kind of lines do they have to be?
Parallel.
That has to be parallel lines, which we also studied back in chapter 4. Well, if they're parallel lines, what does that tell us about the solution?
No solution.
No solution.
Undefined.
No.
Wait, what?
No solution means what kind of system?
Inconsistent. That's what I
Inconsistent.
had to
And
say.
when it's an inconsistent system, does it have a middle name?
No.
No. So there's method 1. How many of you are starting to like method 1 better than method 2?
I kind of like method 2 better.
Method 2. I like to do algebra, so I like method 2. What's a good method to use this time? Should we use substitution or elimination?
Substitution.
Oh, another substitution one. Okay, they're not.
You could do either one.
You could, if you wanted to rearrange that first equation into standard form, you could use the elimination method. But since this one's already solved for y, wouldn't the substitution method probably be most efficient?
Mm-hmm.
So we're going to take y, this equation, 2x, and in place of that y, we're going to put in our other y. What the other y is equal to is the same as, and we're going to solve for x, it looks like. Are those parentheses playing an important role in this one?
Nah.
No, because there's addition in front of it and there's no other number, right? So we can just kind of like ignore them. So what's 2x plus negative 2x? They actually cancel each other out, don't they?
Mm-hmm.
So what do we end up with? 5 equals 1.
Wrong.
True or false?
False.
False. 5 does not equal 1. So we're going to, first of all, before we do that, we're going to say, well, here's what happened. The variables eliminated, because every time you write this, you're starting to plant it to remember it. So the variables eliminated, and we have an inequality this time. They are not equal to each other. Well, if that happens when you're solving algebraically, the variables disappear, they eliminate, and you end up with an inequality. Your brain says, oh, this is what?
No solution.
No solution. So this is method 2. This is what happens. So we say no solution, and what kind of a system? Inconsistent. Okay. Whew, that's a lot of stuff, isn't it? Wow. Questions on this one? Questions on this one? Okay,
5 minutes.
I'm just going to stop my recording and then I can get the notes back up here shortly.